Hey everybody, this is Larry. This is the last day of August. Yay, congratulate yourself. Have a party, have whatever you need. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's farm that I'm going to do live, so watch it at whatever speed you need to do. Okay, find minimum and rotate it sorted array. It is unique. Return the minimum element of this array. This array. Yeah, I mean, obviously you can do it a linear time, and that'll be O of n. You just kind of, do a scan through the loop. But of course, there's also, oh yeah, okay, they actually mentioned this. I missed this. But of course, you can do this on log n time, and this is one that I've seen before. I think there are actually a couple of ways to do this. I think there is the log n one, the maybe more standard log n one of binary search or bisection, maybe more particularly, and then the other one is there's actually a ternary search that is actually kind of cute, and you could kind of figure that out kind of easily after you kind of know that there is a ternary search, if you know what a ternary search is. But that said, I think there may even be a video of me doing this with ternary search, or maybe a variation of this, because I think that's how I did it last time. But I do remember the recurrence, which is, I don't know, it is what it is. But the thing to notice is that you just have to compare it to either the first element or the last element, and then a pivot point, right? The idea is that, okay, you have this point, and then now you can look at the rest of the array, and the rest of the array, let's just say you start with a, let me put it down here so I can kind of visualize it slightly better. Let's say, you know, we took the 4 out, and then now we're here, right? Well, if the number is bigger than our first point, what does that mean? That means that what does that mean? That means that let me think how I want to say it precisely. I mean, I guess there are actually a couple of there are some edge cases I'm trying to think about what's the best way to handle, but they're nothing too tough. The one kind of tricky case is, for example, if it's all sorted, then what do, right? I think you can actually just root out this case by checking that this number, the first number is smaller than the last number. If that's the case, then the smallest number is the first element. We are getting the smallest element, right? Yeah. And then because you have a sorted array, because if you rotate it in any number of times, this number is going to be bigger than that number, right? Because then it's a sorted element. Okay, so let's say we got rid of this, so that we know that then if we have gotten rid of this, then we know that if this number in the middle is bigger than this number, that means that to the right there is a smaller number, because we know that this number is smaller than this number. So then the min has to be between these two, right? So that's basically the idea. And then the other idea is that, okay, if this number is smaller than this number, what does that mean? That means that either this is the min number, of course, or it has to be to the left, because inclusive perhaps, has to be to the left because we know that the smaller number is to the left, because, well, it's either 1 is the smallest number, or or there is another smaller number that's to the left. I think that's basically all I need to do. I mean, I think, we have both partitions and both scenarios. And these are unique numbers, so there's no equal. So I think from that we can go on implementing this. Yeah, okay, so as we said, so we check if nums of 0 is less than the last number, then we just return nums of 0. Because that means that the last number is bigger than the thing, and it's not rotated. Otherwise this is rotated. And then now we take because it is rotated, we know that num sub 0 cannot be the smallest number. So then now we can think about bounds this way, right? So we go left is equal to 1 because we don't count the 0, and right is equal to n minus 1, where n is of course the length of the nums. And then here we just do a regular binary search. I am gonna have to do a binary search video because I think I explained this a lot, and people kind of get confused about how to do it. I'll go over how I do it, and the way that I usually do it. And I go over this is probably like a shorter version of probably what I'm going to do in more detail. Is that okay? The first thing I ask myself is, do I want inclusive or exclusive bounds? I want inclusive bounds, so that's why I choose 1 left is equal to 1, right is n-1 because left we start with left here and right here, and we want it to be inclusive, right? So the while statement is left is less than right. Oops. Left is less than right because if left is equal to right and they're inclusive, that means that that left right is the same number, which means that it's a range of 1 number, right? And that means that that's your answer. That's why I like it like this. Okay. And then mid, we just kind of, for now, we just do this. And I know that there are ways to kind of play around with this with respect to what I was going to say. Oh yeah, I know there's stuff with overflows and stuff like that in certain languages that you can play around with. I'm going to ignore that for now. Also because in Python, I don't have to care. But, okay, so then now if num sub 0 is less than num sub mid, right? What does that mean? As we said, okay, so we just have to think about it. The way that I think about it is just go think about it, right? It's just literally going, I have a visualization, and I have this visualization of, okay, let's say this is num sub 0 and this is num sub mid, and this is bigger. So this is actually the case that we have. Then what does that mean? That means I have to move to the right. And also we move to the right, not including this number, because we know that this number is bigger than it, so it cannot be min, so it has to be moved to the right. And that means that to move to the right, that means that our new bounds, we want our new bounds to be this thing. So that means that we're moving our left, which was previously here, to here, which is mid plus 1. All right. And then else, and keeping in mind that they cannot be equal, so this is just nums less than. So what happens if it's less than, right? If it's less than, well, the current number can still be, okay, this is at the end, so it's a little bit, okay, let's just choose 1 maybe. Maybe I should use the different whatever. But yeah. Well, let's say we're here, this is mid, and we have more, whatever, right? And this is the period, or the mid. Well, we know that the answer has to be within this bound, and this, the pointer, the right can also be, or the mid can also be a possible answer. So knowing that this is our next bound, this is left, so left doesn't change, right is set to mid. And right is equal to mid. And that's pretty much it. Yeah. So then now we can just return, do we return the number or the index? Yeah, so at the end, left is going to be the number, and then now we just return the index, and then we just return the number. Let's give it a spin. Hopefully it should be good. Because I make a lot of silly mistakes sometimes, but that's why we do testing, because so that silly mistakes doesn't sink us. We just keep on working hard. Okay, so this looks good here, and this even has a min case. So I think the only thing I want to test, and maybe it's not even that important, is just a case where the biggest number, the smallest number is the last element, just to be sure. It looks good, so yeah, let's give it a submit. Oh no. Oh, I didn't test the 1 element case. Why does this? Oh, huh. Because this is our bounds, because for 1 element, it's just that I didn't consider it, to be honest. Because this always assumes that there are 2 elements, because we have the 0 and then this bound, and of course here doesn't save it either. So okay, mistakes were made. Edge case is tough. I should have thought about it a little bit longer, but yeah, this is obviously going to be this. But we also want this to be before this, because otherwise this would go out of bounds. But yeah. Yikes. Mistakes were made. Let's give it a submit, and hopefully I don't make another mistake. Okay, cool. Yeah, so it should be straightforward to see that this is this is log n time, because this halves every time. So this is log n loop, and this is all of one cost. So this is going to be all of log n total. In terms of space, we don't actually do anything other than having a couple of variables. So we're Gucci. This is all of one space. And there you have it, all of log n time, all of one space. Yeah, I think this is how I always set up the binary search. Not this template, but in terms of the question that I ask, I think if you have one takeaway about binary search is just draw a diagram of what are you doing and then just kind of reason it through. And once you do that enough times, you don't even need the diagram anymore, of course. But that's where practice makes perfect. Anyway, that's all I have. I'm really tired, so Larry, gonna get some sleep. I'll see you later. Stay good, stay healthy, to good mental health. I'll see you later. Bye bye.